My name is Maria Polonia. I'm part of the team of Marine Environment and Public Policies at Wayback Offshore Renewables. And I've been working for the Megaroller project since the beginning, trying to assess the environmental and socio-economic aspects and impacts of the project. I will be presenting some of the outputs of Wayback's work throughout the project, namely how the Megaroller project applied tools to improve the environmental acceptance of wave energy. So basically, one of the tools that we applied to assess the environmental impact assessment of wave energy and of Megaroller was life cycle assessment. So life cycle assessment is a recognized methodology for environmental impact assessment. The term life cycle refers to any major activities that happen in the course of a product's lifespan. So from its manufacture, use, and maintenance stages to its final disposal, including the raw material acquisition and so on. This means that the tool provides quantification and evaluation of cumulative environmental impacts of a product over its lifetime, considering all inputs and outputs of materials, water, energy, waste. So by including the impacts throughout the product's life cycle, the LCA, this tool, provides a comprehensive view of the cumulative environmental impacts of a product or process over space and time. Moving on to so there are 4 phases in any life cycle assessment that are defined in the ISO standards. All of these steps depend on each other, as you can see in the image. And the phase 4 interpretation doesn't always depend on the actual assessment being finished. It's structured this way because the continuous interpretation of results throughout all the stages helps optimize the analysis as we go further down the process. And so starting with the first stage, goal and scope, here, basically, we define the product system and describe it in terms of functional unit, system, and analysis boundaries. Going to the next phase, life cycle inventory. So the inventory analysis is essentially the data collection phase of the LCA. So basically, we look at all the environmental inputs and outputs associated with the product. Such as the use of raw materials and energy, the emission of pollutants and waste streams. And this is where we get the complete picture. And then moving forward to the third stage, it's called the life cycle impact assessment. So basically here we evaluate how significant these impacts that we've identified in the second phase are. So we make the classification and assessment of all the environmental impacts. So now within the Megaroller project, Wayback applied this methodology to assess the environmental impacts of a general oscillating wave surge converter in an early design phase. The results were expected to contribute to decision making regarding the least carbon and energy intensive design choices, and were then compared with other sources of electricity generation. Regarding the scope of this analysis, there are a few aspects that need to be highlighted. So the functional unit that we've used was 1 kilowatt hour of electricity delivered to the Portuguese grid by one single device, with a lifetime of 20 years. The main results were for carbon and energy intensity, and we assumed a cradle-to-grave approach, taking into account the 4 main components, which are the PTO, the panel, the foundation, and the mooring system. So these were our system boundaries. Usually, and every life cycle inventory analysis starts with a flow chart, which typically so it shows all the main inputs and outputs and processes that make part of the life cycle assessment. In this case here, this is zoomed out. The first stage would be the materials and manufacture. So it includes all the components, or it illustrates all the components and subcomponents that we're taking into account, and also the transport and logistics that are involved in this stage. Then moving forward to assembly and installation. This was the second stage, the second phase that we took into account. That included a pre-assembly and a final assembly of the mega roller, and then operation and maintenance, and finally the decommissioning and disposal of the device. And this is the end. This would be the last stage of our life cycle. So regarding mass breakdown, it's interesting to show these pie charts because, for example, in the first pie chart, we can see a mass breakdown by material, and we can see 6 main materials jumping out of the whole life cycle inventory, with concrete being the most predominant material because of the foundation in this case. The weight of the foundation can also be visible when doing a mass breakdown by subcomponent, as you can see in the second pie chart. And regarding the PTO itself, housing represents the majority of the component's weight just for the PTO. So this is very interesting to start understanding from before the results, which are the most relevant components and materials. So these were the general results that we got for carbon and energy intensity for the device and the system under analysis. We can see, so it's clear that the most carbon and energy intense stage is the manufacture phase, with the manufacture of the foundation having the biggest share, as you can see in the dark blue one. So these were our main results and general results of the LCA. We, in addition to this analysis, and because it was one of the objectives of this exercise, of this task, we also carried out an alternative scenario analysis to try to identify the less carbon intensive design and process choices. So in this case, we decided to model 5 different scenarios. So the first one here is we tried we did a different concrete reinforcement modeling. We also replaced stainless steel by low alloyed steel in another scenario. We tried to see what would happen if all the manufacture of all components was done in Portugal instead of spread out across 4 countries, as per the baseline scenario, in this case the UK, Finland, Turkey and Italy. We also increased, in another scenario, we increased the steel recycling ratio from 50% to 85% to see what would happen. And finally, we increased the system's lifetime from 20 to 30 years. And so these were the results that are normalized compared to the baseline scenario, which is in orange color. Finally, we used previous studies and to compare our results for wave energy carbon intensity with other sources. And although onshore and offshore wind are still in the front line, wave energy, as you can see, is still among the sources with better results in terms of carbon intensity. Finally, to conclude, WaveX contribution to this project on environmental aspects shows the effectiveness of LCA as an innovative tool for assessing environmental impacts of wave energy. We could see that the quantification of impacts helps better communicate results and provides better support to decision making. And also that there is an increase in robustness of arguments when promoting wave energy technologies and environmental benefits compared with other sources to the general public, and also when presenting opportunities for environmental impact reduction to developers through alternative materials and improved processes. Thank you so much.